Just start talking and then I'll start the timer.
Okay, let me make sure I got this working. All right. Hello, everyone. We are Team 228 from California State University Northridge, and we'll be presenting our SAE Aero East Advanced Class Knowledge Event presentation. The presenters today are Victor Paez, Joseph Rinke, and myself, Robert Rodriguez. This year, the Aero East Advanced Class competition will take place in Lakeland, Florida. The design constraints that were to be maintained are a maximum wingspan of 132 inches, autonomous colonist delivery aircrafts, a static and a dynamic payload, and a 750-watt power limiter. The dynamic payload and the CDAs are to be dropped within a 50-foot radius drop zone at varying altitudes, and during this flight, we must follow the given flight procedure. And finally, a data acquisition system that could record altitude and directional feedback. The project approach that we took was a bottom-up management approach. The team was broken down into component-based sub-teams where each sub-team had a team lead. These leads would then report any issues or challenges to systems and integration, who would then report to the project manager. And finally, the project manager would report to the CEO. With this approach, each sub-team was able to give themselves tasks that were to be completed through deadlines, and given the virtual learning environment, we were able to successfully complete all tasks set forth. Below, we see the primary deadline schedule we followed throughout the project. Here we can see the flight procedure that is to be taken during our flight with a legend giving the aero details. We have calculated the best case scenario at 357.30 feet with a 30% margin, making our worst case scenario at 493.07 feet for the required takeoff length. For the landing, we have calculated our best case at 221.53 feet, or worst case at 357.30 feet till a complete stop. The final calculation of the dynamic payload was found through the use and creation of a MATLAB code, as can be seen below. From this, we determined that 7 water bottles and 14 propellers would give a competitive edge over other teams, while utilizing fuselage volume and shape that was developed. An image showcasing our payload configuration and it being housed in a fuselage can be seen on the right of your screen. The static payload would weigh in at 5 pounds, and we will have 3 CDAs with 72 colonists total. Utilizing the MATLAB code, we concluded that landing all required dynamic payload in the drop zone would yield 32.74 points per round, with 5 rounds bringing our total possible to 163.7 points. The system connection design process was initiated by planning and designing each connection between components in the subsystems of the aircraft. System connectivity trees were integral to the systemic design of the aircraft because all components need to be accounted for and designed in a compatible manner. There are 4 major types of connections, including mechanical connections, wired data connections, wireless connections, and power connections. When designing the aircraft, this tree was constantly referred to by all members of the team, where every component of the plane, we performed risk analysis. This was an ongoing process to identify and perform qualitative and quantitative risk analysis to mitigate any possible problems that may occur.
Here are the design considerations for the plane. The team had 3 different options for the wing shape and opted for a rectangular shape for ease of manufacturability and cost. Additionally, the team had 3 different options for the tail design and decided on a boom tail, with the main focus being on stability and control of the plane. For the fuselage shape, we opted for a round loft in the front and a skirt loft on the side due to the payload configuration shape and ease of manufacturability. Lastly, we chose a tailless body design in order to maximize the area and weight, as well as prioritize the amount of colonists in the CDA. Moving on to the moment and CG calculations performed on the plane, here you can see a representation of the moments acting on the plane for different components. Initially, the CG calculations were done using SolidWorks with the results shown in the table. We then decided to calculate the total moment and weight by hand for each of the components to find the CG of the plane and compare the results. The plane estimated weight can be seen below. The equations used can be seen in the figure for CG, moment, and moment arm. The results showed similar values to those of SolidWorks with negligible errors. ANSYS Fluent was used for the CFD analysis of the plane. A turbulent model of K omega was applied to represent the turbulent flow. A convergence criteria of 1e to -6 was used for all studies, including the lift and drag data for more accurate results. All component values can be seen in the table. Some example plots can be seen in the figure above, including wing lift and drag coefficient ratios, the fuselage skin friction drag, and the CDA converging approximately to the same value as the hand calculations. The static pressure and velocity magnitude is also shown with the contours of the wing from ANSYS Fluent. In addition, SolidWorks simulation was used for the FEA of the plane. All components were tested to their respective scenarios. Listed on the table is the material, the failure mode, and if the factor of safety was higher than 1.5 for each of the components. The figure above includes a bending test performed on the wing during cruising to see if the wing would break under the lift loads. The wing was simulated to be fixed to the fuselage, with the lift loads being applied from beneath the wing. Mesh refinement was performed on each of the tests until convergence was met, which can be seen in the plot. After analyzing the results, The FOS was seen to be greater than 1.5 for the wing, meeting the criteria.
Our aircraft's avionics features two main circuits, the first of which includes the propulsion system and flight control system on the left. And during our selection process, we utilized online tools and mathematical models such as eCalc to ensure that our motor and prop combination gave a sufficient thrust output given the power limitations. We also implemented the Gabriel Staples model and references from the Indian River Control Society to identify crucial stability and control functionality of our aircraft. Through this extensive research, these tools allowed our team to proceed with control surface design during vehicle sizing, as well as finalizing servo selection with respect to our vehicle's weight, material, and payload configuration. A new addition to our flight control system this year was a 3-axis gyro stabilization unit, which was integrated into our radio receiver controls. This was useful in preparing our aircraft for varying weather conditions and providing fast control response to different air loads. Once our selections were finalized, all results were experimentally verified during ground testing with the servos, as well as a custom designed 3D printed thrust end for propulsion. The second circuit features the data acquisition system, first person view, and payload release servos in the middle. Arduino-based data acquisition system measures altitude, speed, and payload data, and then transmits this information to the ground station via an RF link on the ISM band. The flight data is then displayed and stored via an Excel graphical user interface. Additionally, the FPV camera system transmits a live video feed from the aircraft so the payload specialist can guide the pilot towards the target area and allow the aircraft to precisely release the payloads. And then the final diagram on the right is a standalone system for autonomous delivery aircraft avionics. These gliders are autonomously controlled through a commercial off-the-shelf solution, namely a flight controller board, which contains an inertial measurement unit and a built-in GPS and compass. The ease of integration of this system, as well as PID tuning capability in the software, were deciding factors in the selection process for the CDAs. And now with respect to testing and validation, our team was able to improvise despite some of the given circumstances. In the top left is a picture of the customized 3D printed thrust stand, which was used to mount our motor and propeller for propulsion testing. In the video on the upper right, there's a stream of our data acquisition system being tested on a flight of stairs as high as 13 feet. Also, a screenshot of our Excel-driven GUI is in the bottom right of the slide. The black text streams real-time flight data, and the Save Trial buttons hold information on screen for the duration of the flight when toggled, such as payload data. And they're displayed in different colors to differentiate as well. And with regards to innovation and ideas for future works, the bottom left picture is an Android tablet GUI, which features a flight path overlay combined with payload information displayed on screen.
For our CDAs, we will have a servo release system mounted underneath each wing and on the tail boom. The images provided showcase how we mount it to our plane. In summary, our CDA will have 24 columns in each one with an overall wingspan of 2.33 feet and a total weight of 8.96 ounces. Ensuring our plane had a stable and easy to assemble connections was a primary goal of ours. For a tail connection, we used 2 carbon fiber rods wrapped in non-slip tape that will be held with brackets. Our wing to fuselage connections will be held down by 14 bolts and 4 flathead Phillips screws. Building our plane came with challenges due to COVID restrictions, but we were able to teach ourselves Fusion 360 and CNC cut every balsa wood component of our plane and assemble it ourselves. The total budget of this project totaled at $11,634, where it came from sponsors, school funding, and fundraising. The fundraising that the team did was through selling t-shirts and stickers. To build an entire plane cost $4,003.26, comprised of both avionic and structure components. A key component we wanted to make sure while building the plane was to have enough money to purchase safety stocks items that would enable us to continue moving forward in the event of a failure of a part. For this, we allotted $4,083.52 to purchase extra building material and avionic parts. We left a miscellaneous budget to account for any tools or hardware needed throughout the project. In conclusion to our presentation, here's an overview of our design. Our total takeoff weight is calculated at 43.95 pounds, consisting of 7 water balls and 14 air fowlers for our dynamic payload, 5 pounds for our static payload, 3 CDAs consisting of 72 colonists in total. Our total measured wingspan comes in at 124.15 inches. The plane was designed around the payload to where we created an airfoil shape for our fuselage. This also helped in creating in generating lift. Our design was cost effective in comprising of aircraft like balsa wood, carbon fiber, and fiberglass rods. With our design, it makes it easy to assemble and disassemble the plane by being able to attach and detach the wings and tail. Here's our poster showcasing our plane design and components. This slide displays our marketing brochure that we sent potential sponsors for our team. Thank you. Any comments or questions?
Yeah, I did have one quick comment. The time I stopped at 9 minutes and 21 seconds. Technically, the the marketing material isn't supposed to be part of your presentation. So you can kind of, for future reference, you can kind of finish the presentation first and then show us the marketing material after.
Oh, okay.
Not really a particularly big deal. Didn't really matter in any way here. Can you go back so I can look at it again though?
Of course. Yeah.
There's actually a lot of information on this.
Mhm.
Okay, thank you.
No problem.
Actually, I want to read all the innovations now too. Maybe you could summarize it for me. What's the biggest innovation you see in this airplane if you had to pick one that's going to make it more competitive than the others?
I think it would be our fuselage design shape, being able to carry the amount of payload that it's able to, and also its ability to help generate lift for our plane.
Okay, cool. Couple questions I have. Were you able to test the CDA, guidance systems, or any of the payload drop in any way?
So we were able to test the avionic components in the CDA in terms of its well, Constantine, it was like it's a gyroscope, or
We were able to test the gyroscope and the stability controls outside of the airplane with connected servos, but we did not actually get the chance to manufacture the CDAs, so we could not actually
Okay.
prove the autonomous flight.
in regards to how much of the CDA we have built, we have about half of it manufactured, or at least CNC cut out, but we're still in the
Okay.
process of putting it together.
So in relation to that, you had listed a predicted flight score early on in the presentation. Was that assuming a perfect accuracy for the gliders and the payloads, or did you assume something less than optimal?
Yeah, so that would be for perfect scenarios that all the
Okay.
payload is in the drop zone along with the CDAs.
Do you have anything, Elizabeth? Or
Yeah, I was just curious about if you guys had a weight buildup, or if you had like a target goal, what the aircraft and the CDAs need to be under to maintain the most competitive platform.
Our initial goal was to allow for some safety, was to at least have 45 pounds be a maximum weight that we would allow ourselves to reach, even though I believe it's 55 pounds for maximum. So we think by giving ourselves that amount of room, if we happen to go over that, we would still be under the requirement.
how did you determine the, I guess the takeoff? Was that just a, like an equation from a textbook, or was it a bit more involved in that?
Oh yeah, so it's based off equations from the textbook.
Okay. And did you cover stability at all for the primary aircraft or for the CDA?
I believe some stability was covered in our avionics portion.
Okay.
Yeah, that was
can
part of
you,
our flight control system that was new this year. Yeah.
yeah, can you go back and show that?
For what we have for stability this year is a 3-axis gyroscope assistance included in our FR Sky S8R receiver.
Did you take any design steps to make sure the aircraft was actually going to be stable, like on its own?
Statically
Like
stable. I think
statically
that's a
stable.
couple. Yeah, I think that's a couple slides back. I remember seeing that very early on in the presentation.
Yeah, I must have missed it.
It was quick, but it was in there. If you guys could just pan back through. There. Systems integration, the very next slide.
Oh, this one right here.
So I see this as being like a CG balance.
Mhm.
Yeah, so for this one, we ended up weighing all the components for each of our parts. And then after finding the moment kind of relative to our datums and then the CG of the plane from SolidWorks, we determined where the CG will lie with the actual weights and moments that are happening on the plane. And the results were basically near identical to what we had for the actual SolidWorks model, with just small errors within each of
Okay,
the
yeah.
datums.
It's a good thing that the CG does not move too much when you release all that payload.
Right.
So your guidance system, in order to get the payloads on the target, is that, I know for the CDA, you mentioned GPS, but for the other payloads, is your system GPS based, or are you planning to use just the camera?
Yeah, it was
Yes.
based off on our FPV camera system. Yeah, for the
Okay.
other payloads.
Okay.
We were planning on integrating a flight path overlaid on a map, as you saw in the innovation section, but we kind of ran into a few troubles and just the time didn't allow us to progress with that idea.
Yeah, I understand that. Since I'm not hearing anything from Elizabeth, I'll keep going. Can you talk
You're
a little
better
bit
at this
about
than I am.
that just means that I just have a list of questions because I'm involved with the advanced class rules development, and I'm always interested to see how you guys tackle the various challenges we put out. But the question I have is related to the how you picked out the optimal combination of payloads to maximize your score. Is that just like because I know you had some static weight in there. What made you decide to keep the static payload in addition to all the other payload types that you can have?
So part of the static payload, along with these calculations, we tried to see what amount of weight and where it would be located in our plane would help keep our CG in place. So that was a big
Okay.
factor that we took into consideration for that.
So it's like ballast, but not ballast because it's
Yeah.
actually payload.
Yeah.
Yeah, we also had a MATLAB code kind of generated to see what was the optimal amount of howlers and bottles to kind of maximize the points, like kind of comparing to last year's scoring. I think
Okay.
we gave ourselves about like 67% success rate to be over first place from last year, from what last year got us first place for their scoring in terms of the payload configuration.
And that was one of the first things that we did initially, was figure out our payload size. And that's essentially how the fuselage shape came about. Was once we figured out what our payload size was we kind of designed our plane around that, since we know that is a big factor in points.
Yeah, the way that it's written is that the glider delivery is like the single most important thing.
Mhm.
It's definitely something we wanted to prioritize. You had a schedule shown very early on with some dates on it. Were those dates the planned date, the actual date, and how did you manage, the uncertainty of COVID and really knowing what you're going to be able to do with the schedule of trying to put this airplane together?
Yeah, so one of our big things that as a team and along with our advisor is we wanted to get a lot of these huge deadlines out of the way early on, such as our preliminary design review and our critical design review. That way it would enable us to take in any criticism that we may have given or suggestions from like who we were presenting it to, and really integrate that in bettering our plane design and having that much extra time in between when our final presentation was for our critical design review to assembling and to our presentation would be able to give the best possible outcome that we could.
Okay. So if the CDR took place in October,
Mhm.
I mean, what have you been doing since then? I mean, has the design still been changing a little bit
Yeah,
on the
so
CDR?
Yeah, so the design changed a bit as we started manufacturing. Um, a lot of a big portion of what took up the gap in between was how do we get around these restrictions that we have, which is thankfully one of our team members had his own CNC machine. So any design that we wanted to test out and see if it would work in terms of connecting them together, we were able to do that.
That is that's awfully convenient.
Yeah, it very
Yeah, a real advantage in that
yeah,
respect.
we definitely took advantage of that given our situation.
Okay, and the last question I've got now anyway is with respect to the aircraft, you know, the aerodynamic surfaces, how did you select an optimal design or optimal sizing? Why is the wing as big as you have it? Why is the tail the size that you have it? Things like that. How did you really select an optimal out of that?
For the sizing of like some different components, it was a lot early on. It was more literature, kind of trying to understand why certain aspect ratios were chosen compared to others, and then after kind of, I guess, mitigating to where we want it to kind of be around, we would test it using ANSYS Fluent to kind of see what kind of values it would give us compared to what we're kind of expecting from literature. So some of the design, I could talk more on the wing, but some of the design considerations were based around like what optimal aspect ratio would give us more lift as opposed to, how can I say it? Yeah, basically we're kind of trying to capitalize on lift as opposed to, you know, generating less drag and kind of trying to be within the size limit of our wingspan.
Okay. So was there like a lot of different iterations of the design that you tried out, or was it just a couple?
There was different iterations. So initially we were dealing with, I think about 4 different airfoils we were testing. Trying to find the right one for our team. Once we learned early on that it was going to be more, I guess we are going to be more ourselves manufacturing as we were trying to find an outsource and we couldn't really find one. We opted to try to include manufacturability as one of also the main considerations for the design, since we knew we were going to have some trouble later on if we had, like, say for an airfoil that had a really thin trailing edge, to try to manufacture that ourselves and all the other cases.
You just mentioned airfoils.
Yeah.
Did you talk about that in the presentation? I've got some people down there. I'm glancing through and I don't see it.
No, we didn't mention airfoils in the presentation.
So you said you're looking at 4 different ones. Well,
Yeah, early on when
which
we were,
ones were they? What did you pick out and why?
so the main considerations for the airfoils were trying to get airfoils that work in low velocity and generate high lift at that velocity. That was our initial kind of inspection for which airfoils to select. Some of them were the GOE, I believe it was 40. I don't remember the exact values, but one of them was the GOE. We have the sleeve we're looking at, the FX. I forget the exact airfoils. FX. Yeah, I can't recall all the
They're
airfoils.
sounding familiar.
Yeah, but around those type of airfoils, we're looking at, they're really compatible in terms of low velocity with high lift. And we were looking at the manufacturability after, because they had comparable results in terms of how much lift they generated for the speeds that they were cruising in. So yeah, definitely initially it was more on the lift and kind of how can we maximize our the amount of lift we're generating for the wing. But then after, we're kind of trying to subsidize with the manufacturability, since we knew we were trying to outsource it and it was kind of hard to find. We couldn't find a place to outsource, so we knew we were going to have to be building it ourselves. So we opted for also adding manufacturability as one of the main considerations for the airfoil.
Yeah, the 3 that I have that we went through for wing consideration was the Epler 423, the S1223, and the GOE 447.
And you compared those with like X-foil or based on wind tunnel data?
Yeah, so a lot of the information that we got was from the airfoil tool database in regards to some of the information that they were populating there.
Okay. Well, the judge just walked out, so she must obviously have not liked whatever that was. I say in jest. Making sure that I have asked every question that I plan to ask. I think that's all I got right now. So I don't want to end anything prematurely in case Elizabeth has something else. So I guess just hang on, and maybe while I'm scribbling down some scores, maybe I'll think of something else, and you guys will conveniently be here.
Okay, yeah, if you want me to reference any slide, let me know and I can go to that.
So I'm basically done with the questions, Elizabeth. So I don't know if you have anything else. Did you have any other questions?
I think your mic's muted, Elizabeth.
I think she's done. You can't actually direct message me if you really had something really important you wanted to ask. All good? Okay. All right. So thank you very much, guys. That's all I have.